Brought to you by Connect.js, Atlanta's premier JavaScript conference. Sponsored in part by FeatherDirect. Need a mobile app? Contact us for your custom mobile solution.
They did make an announcement earlier, but obviously this is not the Angular boot camp, and you would not want to hear me talk about Angular anyway. I know next to nothing about it, so I claim no pride in that. So anyway, we're going to go ahead and get started. Now, just to forewarn you, this is an hour slot, but the talk is not at all an hour slot, which means we'll have plenty of time for questions afterwards. But that means we're going to take this at a little bit of an accelerated pace, and there may be that awkward space at the end of the talk where everybody's wondering if they should start scooting out. I will not be offended at all. So provided you're in the right room, we'll go ahead and get started. So this talk has nothing to do with Johnny 5 or any of that. That really was just marketing strategy to get you guys in this room. So this talk is actually a little bit about something else. But before we get into that, let me tell you a little bit about myself. I work with Big Nerd Ranch. It seems we've kind of taken this place over by storm, or at least this room today. So I work with our Rails and front-end department as a consultant and instructor. So unlike a lot of the people I've given this talk to before, you guys are not across the Atlantic Ocean, so I don't have to tell you that you'd have to fly over here to take one of our boot camps. So we are actually just about an hour right now out in the middle of nowhere in the woods, and we'll be moving to Callaway Gardens next year. So if you want to come learn anything from us, Android, iOS, design, JavaScript, of course, Ruby on Rails, any of that awesome stuff, we'd love to have you. Now, I love type coercion in JavaScript almost as much as Ruby scopeless for loops. If you take offense with any of those opinions, just mention me on Nibbler or whatever, and we can dish it out, all that fun stuff. So you guys, presumably, if you're in the right room, came to hear about machine learning, but I really lied to you. You actually have come to the wrong talk. This talk is actually about a very large number with a currency attached to it. So how would you like to build a small round box with a buddy in the garage, of course, that does nothing but modify the air temperature in your house or room, depending on where you install it? It seems like a big deal, right? Well, what if you made it self-regulate that temperature throughout the week? Well, apparently, Google thought this was a pretty awesome idea. They thought it was a $3.2 billion idea. Who of us is not envious of this awesome acquisition story? So apparently thermostats that know when to bump up the temperature a degree or two without your owner's intervention are important to the customer populace, or at least it is to the company that's going to acquire you, and thus it should be important to you, because who doesn't want $3.2 billion for their tiny little garage project? But honestly, I lied to you again. This talk is not about thermostats or $3.2 billion. It's actually about people. Now, honestly, people is somewhat of a large demographic to cover in this short amount of time, so we're going to narrow it down to this one person. Everyone remember this? The beloved actress Lucy from the I Love Lucy show. Since this talk is actually in the US, I don't have to educate my European audience about who she is, but this beloved actress has entertained us throughout the years with all of her classic predicaments. Well, one in particular was every time she wants to go out to eat, which, if you watch the I Love Lucy show, is incredibly frequent. And she, being her decisive self, always knows where she'd like to go to dinner. And hopefully, we have audio.
Oh, darn it.
As you were, Diners.
I just happened to think we ate Italian food a couple of nights ago.
Well, naturally, as decisive as that was, she's even more decisive when it comes to dinner.
Lamb chops, huh? Gee, that sounds good. They're not fattening either. Would you mind changing my order to lamb chops?
2 lamb chops.
That's 2 for each of us.
Well, since it takes her so long to make these decisions, and for those of you who have seen the show, it takes about the period of half an hour, 30 minutes, for all these decisions to unravel. So honestly, this whole talk about aesthetics and image aesthetics has secondary importance compared with her crisis. So really, we're just going to drop this talk entirely and see what we can do to help her out. So how could we do this? Whenever Lucy makes decisions about where she wants to eat, we might pull out a whiteboard and see if we can make some sense out of what she eats. So that way, next time before we go to a restaurant, we can decide what she would otherwise order and just tell her that. Well, one classical way we could do this is with a decision tree. Now, a decision tree is just, in this case, it's a binary tree, but it doesn't have to be a binary tree. It's just the traditional structure, and it splits on particular features. And we'll find out in a moment what kinds of features. But features are interesting because what we could do is if we had a whiteboard out and we took note of all the things that happen during the time Lucy's making up her mind what to eat, we might notice that some of these features influence her decision. So for example, we know that Lucy will get whatever the others tend to order. So we could branch on what, say, Ethel decides to order. She decides to go with lamb chops. So it's likely that Lucy, unless Ethel or unless some of the others tend to order, it's very likely that she'll order lamb chops as well. Now, on the other hand, if Ethel doesn't order that or doesn't order at all, it's likely Lucy will stay with her decision. That kind of data makes a lot of sense as this sort of decision tree. So in this diagram, every single feature is something that we're branching on. Those are the F's in here. And then L is this mysterious label. So let's talk a little bit about what that is. But the intuition for this, or what we'd like to do, is we'd like to automate building this sort of tree. We could have built this ourselves. We could go watch I Love Lucy over and over again and look at all of her dinner decisions and figure out what her decisions would be and try to build one of these trees ourselves. But this is really time consuming. And furthermore, we might want to use this to help other people. What if we wanted to help Ethel decide what to eat for dinner?
Now let's see if I've got this straight. Lamb chops for you, sirloin steak for you, pork chops for you, pork chops for you, and a new eraser for me.
You know, with all this talk about pork chops, I think... I guess I'll stick to lamb chops.
Well, so much for that. I was hoping we could help her out, but apparently her decision tree is fairly simple. So what if we could observe Lucy every time she went out to eat, making these dinner decisions, and we could observe it on several different occasions? Now, of course, in our attempt to get some funding from Y Combinator, some of these other big companies, we have to throw a lot of terminology on otherwise simple concepts. So we might call every time she goes out to dinner an instance. And an instance, for its complex terminology, is really just every time she goes out to dinner. Big deal. Well, at every instance, what we might want to observe are some things that we think will influence her decisions. We might call these features. So features are just anything that we think is probabilistically correlated or might influence the end result. Now, naturally, we should ask ourselves, what is that end result going to be? Well, that end result is what we're going to call the label. So in our I Love Lucy example, every instance is every time she goes out to eat. Every feature is everything else, what everyone else is going to order, because we tend to think that it might influence her decision. The label would be what she finally ordered. In the case of the video, pork chops, because Ethel does not win out with her vote on lamb chops. So between the instance, the features, and the label, we have a description of every time Lucy has gone out to eat. Now from that information, we might be able to generate some usable model of some sort, maybe another decision tree, that will help us predict what she'll order in the future. And this is the canonical machine learning problem. It's called classification. So given a mapping of these instances to labels, it's actually really simple to build this tree, provided that we have a unique feature set for each of these instances. In other words, we don't have the same sets of features that produce different labels. Or in other words, depending on what these others order, Lucy always orders the same thing for the same choices of her companions. So it's really easy actually to write an algorithm that builds one of these decision trees that exactly predicts every one of these decisions. So we would call this a perfect fit. Now this seems useful, except that our end goal is to help Lucy make these decisions in the future. That means that we might come across a decision that she has not yet made, that she has never had the opportunity to make. Maybe she's in a different restaurant. Well, in that case, our perfect fit is not necessarily going to give the best output. So we have to ask ourselves, what makes a really good tree? Well, it may not be a perfect fit. And in fact, this is very frequently the case, because anytime we do these very tight fits to the data we've seen so far, it doesn't usually generalize very well. Now, there's a synonym for generalize. It's simplification. So we've kind of inherently biased the types of decision trees we're going to like better. We've inherently said that a simpler decision tree is probably the better solution for the future. Now this assumption, just because we're trying to get more funding, we could arbitrarily slap a title on it. We'll call it Occam's razor. And anytime we make an assumption about which kinds of decision trees will be better for the future, we'll just call that an inductive bias, since we're on a terminology roll. So in other words, what we want to do is we want to build a decision tree that generalizes well to the future and thus is the simplest. Now in the case of a decision tree, that probably means that it's a very shallow tree and has very few nodes. So there's a bunch of different ways we could try to do this, but here's one way that we might try to do it. We could try a divide and conquer approach. So with this sort of approach, what we want to do is divide the set of all instances. In other words, if we took all of the times Lucy's been out to dinner, we would call that the instances, or instance set if you want to get more mathematical. And what we'd like to do is we'd like to split that instance set in two, where each subset has the exact same label. So in the I Love Lucy example, we want to divide this into all the instances where Lucy has ordered pork chops versus all the times she has ordered lamb chops. Now, ideally, we want to find some feature that we observed when she was eating out that exactly does that cut. So for example, if we found that what Ethel ordered is always what Lucy orders, it's very easy then to make sure, or to split all of Lucy's dinner decisions exactly in half, just based on that one feature, what Ethel ordered. Now this is very rarely the case, so what we would want to do is start out the root of the tree on the feature that best separates all of the instances that have been seen so far. Now, it's kind of hard to describe that, but there's some actually better mathematical ways to put it. It's called entropy. So entropy is a measure of randomness, which means that high entropy means that the data is highly random and thus very hard to predict, whereas low entropy is far less random. And at the extreme, an entropy of 0 means that it's completely deterministic, or constant if you prefer. So what we'd like to do then is pick whichever of these features most reduces the entropy of the two resulting subsets. In terms of the label, we want to reduce how many labels show up in each subset. So it kind of makes sense. It's a little bit weird to think about at first, but it's probably a more intuitive way as opposed to building up a decision tree that exactly matches the data. So what we could do is for every single level in the tree, we just pick a feature that we want to split on. So at the very top, we might decide that Ethel's decision most likely influences Lucy's decision. So we would start at the tree. Let me go back for a moment for that visual. So we might start at the first node in the tree, and that first node in the tree might be what Ethel's decision was. As we get lower in the tree, we start picking other features that had less influence, but still help us cut up the instance set appropriately. So that algorithm actually is not our own. It's called InfoGain. That's actually the heuristic that's used for splitting. The entire algorithm is often called ID3 CART. There's a lot of variations on it. And it's a very useful and relatively easy to implement algorithm. The only problem is that it always selects the best attribute at any given point to split on. That seems reasonable enough, but for those of you familiar with the characteristics of algorithms, picking the best attribute at that given point in time is not always the best decision. Perhaps that decision would have been better put off further down the tree. So that sort of algorithm is called a greedy algorithm. And in the case of the InfoGain heuristic and ID3, it's actually not always going to produce the simplest tree. So what that sometimes means is that for given data sets, we'll get really, really complex trees that perhaps have 1,000 nodes on the right side and just a few on the left side. So it's also a very unbalanced tree. What we would like most is to have a very shallow little tree that only depends on a few features. So the simpler the better. Unfortunately, ID3 doesn't always get us there. But it's useful. It's better than starting from nothing and trying to figure out Lucy's decisions on our own. So now that we know how to build that tree, at least from a theoretical point of view, how could we actually go about training it? The naive way to do this would be to give this trainer all of the data that you've seen so far. So if we watch the I Love Lucy show, all 250 or so episodes of it, we might see her go out to eat probably around 200 times or so. That's quite a few instances. We could pass all of those straight in to the trainer, and the trainer would just try to figure out which feature to split on, etc. Now, this is nice, but recall that it's going because we've trained all that information on it, it's possible this decision tree will exactly match all of these instances. So we're not left yet with any data that lets us confirm how well does this generalize to the future. Remember that our end goal is to come up with a decision tree that we can use for its predictive power. So what we should probably do is take some of the training data, maybe like 80% of it, and we'll use that when we're training the algorithm. Then we'll save about 20% of the data that the algorithm has not yet seen, and use that just for testing purposes. So if we run this algorithm on 20% of the testing data and find that it is 95% accurate at figuring out what Lucy's going to order, great, that's awesome. If it gets more like 70%, that probably means that it came up with a perfect fit, and thus it's not going to generalize very well. So maybe we need to investigate some other algorithms. Well, since decision trees really weren't all that incredibly difficult, and now you've got Y Combinator looking for places to fund, for those of you who have followed up on Thelmic Labs funding, we really need to come up with another algorithm. We need to come up with something that's a little bit more, a little bit harder to grasp, of course, and has a cooler name. So in our pursuit of that, why don't we try something that's related to the human brain, naturally? We are the greatest machine learning machines out there. So naturally, let's see if we can teach our computer a thing or two about it. So after wrestling with names late at night while trying to adjust to the current time zone that's 30 minutes down the street, you naturally decide on using neurons in the name, of course. But unfortunately, neurons aren't much used by themselves. You really have to have a lot of them. So let's call it neuron networks. Great, ship it off. Except the adjective form sounds more interesting. Let's call it neural networks. Getting closer. The problem is our financial advisor comes to us and says that our investors don't want us to think we're actually using brain matter in any of this. So we're required to call it artificial neural networks. Great, we've come up with an algorithm in a few minutes. Completely original. So here's how it will actually work with a neural network, artificial neural network, excuse me. So in an artificial neural network, we have several different components. So every single neuron in here is represented just by a circle. It's got a little p on there, which doesn't make much sense because we're calling them neurons, so it should be n. Well, it turns out our advisor required us to come up with another name and told us we had to call them perceptrons arbitrarily. So unfortunately, we have to do p as opposed to n for neuron. And every single one of these perceptrons has wires coming into it and wires going out of it. So this is kind of like a data flow algorithm, or data flow diagram. We have inputs and outputs, and it flows from left to right in a feed-forward style net. Now each of these inputs to every single perceptron actually has a weight associated with it. So the input to any one of these perceptrons could be one of your features. So revisiting the decision tree, this could be what everyone happened to be ordering, and that could be an input to the perceptron. Or it could actually be the output from another perceptron. So you actually can make these networks of perceptrons, and that's where the power in neural networks comes from. So every one of these perceptrons has a weight associated with each of these inputs. If you look at the ugly little formula down at the bottom, that's just shown as a multiplier on every single one of these inputs. So we could decide, for example, that feature 1, what Ethel orders, has more weight on what Lucy will eventually order, so we could give that a higher weight. Whereas feature 2, what Ricky happens to order, could have a much lower weight. So once we come up with this, we see it's really just a weighted average, except for one last part. Notice that this is y equal f of x. It's a function. That function is called the activation function. Now, an activation function is just any function that is nonlinear, monotonically increasing. Not all that crazy, right? Well, this could just really be a square wave or a hyperbolic tangent, as shown in this graph. So we should immediately ask ourselves, why have we complicated this up? Why does our activation function have to be nonlinear? Why do we have to bring back all this algebra nonsense? Well, let's consider if we had a linear function here. So in other words, we take our weighted average of all the inputs, multiply them by the weights, and add them together, and then we plug it into a line. Well, if we plug it into a line is really just a multiplier with an offset. And let's just think about it in terms of a multiplier. Well, if it's just a multiplier, we could actually just increase the weights to all of the inputs to get the exact same behavior. And furthermore, our entire network, because it's just a bunch of linear sums, well, if you sum linear sums, that's just another linear sum. So in other words, our entire awesome neural network has just been reduced to a line in some multi-dimensional space. That's not very useful, and it doesn't let you capture a lot of the types of functions you would see. So if we keep it nonlinear, which just means it isn't straight, and monotonically increasing, which means it never decreases, that's just by convention, then it's much easier to actually imitate these functions. So this is all neural networks really are. Neural networks are just a way of describing functions in such a way that they're discrete, and we can train it, which in a moment we'll see how we could potentially train it. So there's a few different things to note about a perceptron. So as we saw in the network, they can all be connected to each other, and they have all these associated weights with them. So when we're training it, we have a lot of parameters in flux. So the first question we need to ask is, for a neural network to be useful, what are we actually training about it? With a decision tree, it was actually the structure, how we were splitting on features. That determined what behavior the decision tree gave us. In a neural network, we actually establish the network beforehand. We come up with how many perceptrons there are, how they're connected to each other. We come up with that all beforehand. So the actual training aspect comes in selecting these weights, these multipliers on those features, trying to decide which feature contributes more to the input or the output of a particular perceptron. So there's a bunch of different algorithms out there. The one that you guys may have heard of is backpropagation. There's one that it's loosely based on. Backpropagation is kind of a simplification of gradient descent. Now what that means is, let's just start out with some random weights for our entire network. And then let's run a few training examples through it and see how good the prediction is. Now if it's random weights, of course it's going to be junk. But what we can do is take note of how if we slightly varied the weights just a little bit, we can take note of how the prediction changed a little bit. Now, that actually gives you enough information to produce a cheap gradient, since it's a little bit hard to do the differentials and all the craziness you'd otherwise have to do if you were solving this symbolically. We don't want to go to that level. We don't want to be that complicated. We're just going to be cheap. We're going to slightly adjust the input, see how the output changes, slightly adjust the weight, see how the output changes, and from that we can compute this funny mathematical function called a gradient. From that gradient, we just start moving in the way which should reduce the error between what we expected, in other words, revisiting I Love Lucy. If it predicted that Ethel ordered pork chops, and in our little visualization, pork chops was the number 4, and instead it outputted 3, we can compute the difference between those two and say, oh, it should be 4, but it's actually 3. By computing the difference, we can actually figure out which way we need to move the weights to get closer to the optimal solution. So gradient descent is very useful, and it's essentially how backpropagation works. Backpropagation, though, is more efficient. So the problem is backpropagation, or gradient descent, very often gets stuck in what are called local minima or local maxima. Say you're running in your neighborhood, and it's very hilly. And you keep running, and eventually you get to the bottom of the hill, you start panting. You realize you're at the bottom of the hill, and you realize that you're starting to go back up because it's getting harder to run, and as you look up, there's a towering mountain in front of you. That's obviously, you've reached the trough, and you're about to go back up again. Well, the problem is you don't know if 2 miles down the road, there's actually a trough that's lower than that, so you don't know if you'll have a higher hill to climb, unfortunately. Well, that kind of problem of not knowing where the lowest trough is means that our gradient descent could actually get stuck in one of these troughs or these local minima. To get around that, we just add a little randomness, which means whenever we get to the bottom of a trough, or in other words, whenever we come up with a set of weights for this neural network that produces the best predictions, we just readjust the weights randomly. We start over again, and we run the algorithm again, and we see if the output from that happens to be any better. Now, we have to come up with a fancy term for this for the sake of Y Combinator. We'll call it stochastic gradient descent. So neural networks are certainly more complex to wrap your mind around, but they're actually in some ways more powerful than decision trees, because a neural network using this sort of activation function can actually be an arbitrary representation for any function, provided you have enough perceptrons in the network. There's always that little catch. So neural networks are a little bit more complex, both to build and to train, but they're better able to represent arbitrary functions. And if you think about it, that's all machine learning is, at least in classification. We're trying to figure out what function maps from some input to some known output. So that way in the future, if we have an input but an unknown output, we can plug it in and get that output. So machine learning is just about building these functions. And neural networks are really good about being able to produce any kind of function, provided you have enough perceptrons. The problem is, since you have so many perceptrons, unlike the decision tree, neural networks can take a long time to train. So that often means that depending on the problem at hand, you may not be able to use this in any kind of real-time situation. You might have to spend years trying to come up with a really, 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 really good neural network that's also incredibly efficient. So it's no picnic working with neural networks. That trade-off is so strong that really we should give it another name, and I was very glad to hear it mentioned in the previous talk, actually. It's called the no-free lunch theorem. And the no-free lunch theorem simply states that there is a trade-off between simplicity, in other words, how simple that classifier, like our neural network or decision tree is, and its representational power. In other words, how many different kinds of data sets it can predict. So ideally what we'd like to do, based on Occam's razor, is come up with whatever function or use whatever classifier is the simplest. So if decision trees do a really good job of describing our problem and predicting the output, say in the case of Lucy, then we want to use that. It doesn't make sense to bring in something more complex like neural networks, because that's going to take more time to train, and it's also going to probably overfit the data, which we don't want. So now, thanks to Lucy, we have two algorithms. So perhaps we could revisit the original punchline for this talk, because I lied to you again. I actually did not lie to you that I would not talk about aesthetics. I hope you followed that, because I did not. So what we'd like to do then is try to apply some of this to making computers a little bit more aesthetically intelligent, or maybe just being able to pick out better pictures. And that's exactly the application we're going to use. So the first question you should always ask yourself when dealing with a domain that you don't want to hand code is, what is my data set going to be? Well, if we're talking about aesthetics, we're probably talking about images of some sort or photos. And in fact, that is going to be our data set. We're going to have, in this case, 3,500 images, and we want to say something intelligent about them, that an artist would say about them. Now, what exactly an artist would say about them, we'll cover in a moment. So that's what our data set will be. But the next question you should always ask is, what are my features? Now, in I Love Lucy, the features were what everyone else ordered at the table. Well, in the case of an image, it seems logical that every single pixel in that image could be a feature, because they all contribute to the image. So for example, you could have a separate feature for the red, green, and blue channel of every single pixel in the image. And some of you are sitting there laughing at me saying, oh, that's nonsense. But it's actually a very useful approach, and it's actually really commonly used in text recognition, OCR. I'll show you guys a demo later. So it actually is very useful. The problem is we have to make sure that we normalize all our data. We have to make sure that all of our images have the same dimensions and that they all have the same resolution. And furthermore, it'll take an eternity to train the network. So we really don't have that much time. Y Combinator has some big grant set aside for us if we can get this problem finished. So in the interest of time, we don't want to do that. What we'd like to do is just take some rules of thumb. So this is where machine learning especially excels. Anytime you have a rough idea of what contributes to the goodness of something, machine learning allows you to train a network based on those and come up with the exact weights needed to come up with some prediction. So for example, in the case of Lucy, we could have whiteboarded it out and figured out what the decision tree for dinner decision was. Instead, we decided what are the interesting features that we think help predict the output, and then just let the computer do the busy work. So we could do the same thing here. So on the one extreme, we don't want to hand code all this. We don't want to write code that tells you how good an image is without doing any sort of training. That would be a royal pain. I've tried it before. Well, instead, what we don't want to do, though, is have every pixel in the image be a feature. That'll take too long. So let's take the middle road. Let's figure out some algorithmically feasible ways of coming up with some numbers. And these numbers need to be probabilistically correlated with how good we think an image is. So I'm doing a lot of hand waviness right now, but there are actually solid algorithms, as we'll see. So we need to go on then to what our features will be. So let's pick a few. So the first one that I would pick is composition. Now composition is a pretty broad feature, but one of the best known concepts of composition is the rule of thirds. So good composition just says that your points of interest, the things that are most important about the image, should be on the rules of third intersections in an image. Now this is actually not the exact case. It's actually the golden ratio. It's a minor technicality because they're almost exactly the same. So we almost always use the rule of thirds. But if you want to get really technical, it's the golden ratio. Everything in math, everything in aesthetics is the golden ratio. So as long as we keep the points of interest far away from the middle and not too close to the edge, that's essentially all the rule of thirds says. So those of you who have avatars up, the other speakers in here, I've probably looked at all your avatars and laughed at how your head was exactly in the middle of the image. Rule of thirds would say move it over just a little bit. So rule of thirds is very helpful, and it's actually fairly easy to compute, as we'll see in some other features along. Now, good photos also emphasize a concept called loneliness. So loneliness says that a good photo should really only have one or two subjects or points of interest. So an image with too many points of interest is distracting. So for example, this picture here, link cited below, has a lot of detail in it. There's a lot of texture in the water and there's a lot of texture in the sky. There's also a lot of interesting colors. But the human eye is naturally drawn to the boat. And that's because we naturally look at the boat and say, oh, that's one thing. So we would say that there's one important thing in this particular image. So we would call it loneliness. Now, this particular image, it's kind of easy to come up with an algorithm that can compute where all these lonely points are. But it's a little bit harder than something like composition. Because what if we had a picture of a beach extending out into the distance, and we had one person standing on the sand way, way, way far back? The computer wouldn't see the person. It would just see a few pixels. Whereas the human eye naturally says, oh, that's a person. So admittedly, loneliness is a much harder feature to come up with an algorithm for. But it turns out you can come up with some pretty close approximations. So moving on from loneliness, simplicity. Simplicity is very similar to loneliness on the surface, except that simplicity is focused at the micro level, whereas loneliness was focused on macro. In other words, it was focusing on very large parts of the images. Simplicity is actually looking at things like texture. So in this image, for example, the background is very smooth and blurry because this particular image was taken with a very low depth of field. Well, because of that, the image, or the subject, in this case the cat, stands out from the background. So simplicity is useful because it helps you differentiate what's important in the image from what isn't. But it doesn't concern itself with how many importances there are. It doesn't try to count out how many bits of texture there are in the cat's fur. It just tries to say what parts of the image are simple, which parts are not simple or complex. Now, the interesting thing about simplicity is that you can't just correlate it directly with the goodness of an image. For example, there are parts of this image that are very simple. And I could say that an image with a lot of simplicity is very good. But if you didn't have the cat in here, which is very non-simple, I would probably say this is a pretty poor photo. So really, you have to have a balance. You have to have some areas that are simple and some that are not, which means that our machine learning algorithm needs to have some awareness of locality. Now, kind of related to that, contrast. Whenever someone's looking at your photos on Flickr or Facebook, they're probably looking at thumbnails. They're not looking at the full-size images. So if you want anyone to click on those pictures, naturally you want an image that pops even at a small scale. Well, it turns out that's actually a really good rule of thumb. Anytime you're trying to pick out good pictures or good compositions or good colors, you want to make sure that at the size of a thumbnail, it captures a user's attention. So here's an example, and it's very popular in black and white photography. So the original image here, for example, probably didn't have as much contrast between the light and the lady walking up the pathway. But by enhancing the contrast a little bit, that helps separate the subject from the background. So it's similar to simplification, which helps separate the subject from the background in terms of how smooth or complex an area it is. Contrast does it by luminosity of the areas. So contrast is also interesting because it doesn't depend on colors so much. A lot of times nowadays, we take a picture and it's covered in lush colors, and we think it's a great photo because there's so much color. But then if you convert it to black and white, we see that it's pretty much flat. There's not much contrast. The images with best composition look really good in black and white, generally, and colors are often just an add-on. So our algorithm should take into account that sort of rule of thumb. Now, there's one final rule of thumb that we might want to investigate, color theory. Now, this is one I honestly tried to hard code, and it was very difficult, and it turned out the results weren't so good. So machine learning could probably do a much better job. So with color theory, there are a lot of different rules about what colors look really good in an image together. So for example, in this image, we see there's a lot of different colors in here, oranges, purples, greens, and yellows. The key is that they all have a certain harmony to them. So for example, you'll see that there's warms balanced against cool colors, warm being yellow reddish colors, while cool would be bluish greenish. So warms versus cool is a really handy technique. It's a really handy aspect in color theory. There's also complements, so we might notice that some shadows have certain colors. We might also say that two colors arbitrarily do not look good together. In a lot of cases, solid red next to solid green looks pretty ugly, whereas purple next to orange looks great. So there's a lot of these kinds of rules that we can generalize from color theory. The good thing about it is that colors are just numbers, so we can train on that sort of stuff. Now, a lot of you have probably been thinking, okay, how on earth would he intend to implement this sort of thing? This is all really hand-wavy. Well, I kind of skipped over an implementation detail. So a lot of these features, I mentioned that locality is important. And the way we can work locality into this kind of training is with wavelets. Now, wavelets are kind of like a frequency transform for images. So those of you who are familiar with the Fourier transform, you might be used to doing that in signal processing of some sort. Well, wavelets are kind of like that. They do a similar thing, but they have very different characteristics. And wavelets are useful because they can help you take parts of an image and probabilistically decorrelate them. Now, all that means is back when Lucy was making her dinner decisions, maybe Fred's dinner decision is based on Ethel's decision, and Lucy's decision is based on both of their decisions. We could say that Fred's decision is probabilistically correlated with Ethel's. Now, the best features to an algorithm should be independent. In other words, Ethel's decision could be, or Fred's decision should be completely independent of Ethel's decision. That gives us the most information. So wavelets can help us decorrelate parts of an image from each other, which generally parts of the image are highly correlated with each other. For example, if you took just the center of an image and you tiled it out across an image, and then you did a diff of it with the original image, the error wouldn't be that great, actually. They would be pretty similar. So wavelets, the wavelet transform helps you decorrelate these so you can just have better features. The key part of wavelets is that it splits up the image into sub-features, into these little localities, which means that we can not only train on how good the color theory is, we can train on where it appears in the image. For example, we could say that the borders of an image should generally be really, really dark, whereas the center of the image should be light. This would be vignetting. So those sorts of things, all of those different factors that we explored can benefit from something like the wavelet transform. All right, so it seems like we have enough feature here. We've got 6 or so features, and we can split them up into 16 or 64 squares with wavelet transforms. Now we've got maybe 250 features. Seems like enough to train on, right? So we could go do this, get $3.2 billion in funding, right? Unfortunately, we're a little bit late to the game. A research group from Pennsylvania State University actually did this already several years ago. They put together an excellent paper, which I highly recommend you go read. The link is up here. They put a paper together on computing these various types of feature extraction, and then they trained with only 56 of them. Now, the interesting thing about this is that every single one of these features was, in a sense, a rule of thumb. It was some way that an artist could say, well, most images have really good contrast right where the subject is. These very vague rules of thumb can sometimes you can sometimes put a number to them. And if you can do that programmatically, you can run it through a machine learning algorithm and try to come up with some way of making use of that rule of thumb. Now, in this particular project, they actually used support vector machines, which actually have some very similar characteristics to neural networks, but the two algorithms only share some aspects. They can produce some different results. For some data sets, for example, SVMs can train much faster, and they yield a simpler classifier. Recall that simplicity is the goal of all this because we want it to generalize to the future. Now, what was their data set? It was 3,500 images. They just nabbed it from photos.net. Now, the interesting thing about photo.net is that they have human ratings. So they have star ratings. which means we have the instances, which would just be the image. We can compute the features, presumably. It's a bit CPU intensive. And we have the labels, which would be the stars. So with that data set, they were able to train an algorithm that came up to around 70% accuracy. Now, 3,500 images is actually a pretty small data set, and they only trained with 56 of those features. There were more like 200 or 300. So 70% accuracy is astounding when you consider that if they took any of those features and tried to use it to predict how good the image would be, it only came up to 50% accuracy. So machine learning is very good about being able to take these rules of thumb, which normally don't do very well on their own, and building them up. So the greatest success story of this would be spam catching. So some algorithms like neural networks and decision trees are actually overkill for catching spam. If you can come up with some rules of thumb, like for example, one piece of spam mail is more likely to be spam if it's all caps or it has certain words in it. Those rules of thumb by themselves don't do a great job. But if you can train in a network or train a support vector machine or whatever with them, it can produce great results. In particular, boosting algorithms do this sort of thing. A really popular one is called AdaBoost. So those of you who are looking to implement spam catcher algorithms from scratch, you should go check out AdaBoost. So 70% accuracy may not seem incredible. There's still room for improvement, but that really is by no means shabby for something that started out as a cheater's guide to dinner. Now, as part of the no free lunch theorem, neural networks need many more examples and take much longer to train than a simple structure like decision trees would be. This is one of the gotchas due to the no free lunch theorem. And it also takes a good bit of experimentation to come up with really good parameters during this training process. So for example, there's the learning rate and the momentum rate. Whenever you're training up a neural network, when it's climbing hills or descending down hills, you can tell it how quickly it runs down the hills versus how slowly it should be going, or how quickly it learns from its mistakes, as it were. Those two parameters need a lot of fine-tuning. So machine learning, like many fields, is really an art with a lot of brushes and paints, and hunches on which algorithm should be used are invaluable. So in the case of the learning rate and momentum parameters, at the cost of accuracy, you could increase the learning rate. In other words, you run down the hills and run up them much faster. Or you could try to get more accurate. You could take your time walking down the hills and do a little more exploration, which will take more time. So if you know enough about your domain, if you understand the data set and the attributes of these algorithms, you can come up with a better classifier that's simpler and comes to the solution much faster. This is the artistic part of machine learning, is basically just playing around with these parameters. Now, for the mere mortals among us with a lot of time on our hands who really don't want to spend all this time tailoring all these algorithms and trying to figure out how to implement them all in JavaScript, you can use ensemble methods. So ensemble methods it's an interesting term, but it really just means take all of the algorithms you know and apply them to the same problem, and then do a consensus. See how many of them output one thing versus the other, and pick whichever thing is output the most. And this is in fact what the Jeopardy computer Watson used. It would use thousands of algorithms simultaneously, running them in parallel, and then it just picked the answer which most algorithms suggested with highest probability. So that's kind of the throw hardware at it solution. But if you want really good results on a small machine, that's where it helps to start tuning these parameters. So by now, you're probably ready to apply machine learning to your own problem in JavaScript. This is, after all, a JavaScript conference. So what does the JavaScript community have to offer? Well, if neural networks fit your needs, and again, you want to make sure it's not too complex, you might try out something like brain.js. Now, brain.js is great for getting started with machine learning because it has a really easy-to-use interface, and it lets you stream in training examples, which is really a must if you're working with these really large data sets. So here's an example of how you would create a neural network in brain.js. Hopefully you guys can see it, probably not, but it'll be on video, I believe. So after you create a new network instance, you just train it up with either an array of instances, or you can pass in one at a time. Now, what you pass in, everything that you pass into this network has to be an instance, and every instance is features plus a label. So what we can do is we can pass in this example, a contrast example. So this demo I'm showing up here, I'll live demo in a moment, is a classic problem. You're trying to determine what color of text shows best up on a particular color background. Now, there are actually mathematical algorithms or There's just math formulas. You can plug it in and determine if you should do black or white. But it turns out it's a really good machine learning problem. And in fact, this is brain.js's great example. So in this example, our feature set is the red, green, and blue components of the color, and the output is whether we should put black or white as the text color. So there are many different ways we could have broken down this problem into instances. This is just one of the easier ways to do it. We have red, green, and blue all as features. And notice that they're all numerical features, and they're all between 0 and 1 in this case. You can actually, I believe with brain.js, you can put in some unnormalized data, but it's usually accepted practice to do something like between -1 and 1, or to do some sort of normalization. Now, once you've actually trained that network, the actual useful part about it is to run that network on some instance you haven't yet seen. So in the case of this would be if you're running your website and you want to see if you should show black text on top of a particular color blue, you would just run the color blue through that network that presumably you had pre-trained, and it would say whether you should use black or white. Now, because it can take a long time to train these networks, what you want to do is serialize it and save it off for usage later. Well, the only part about a neural network that changes is the structure and the weights. So in the case of brain.js, it actually has a toJSON function, so you can serialize it and rebuild this network later on, so you can run it on whatever color you happen to be facing. Now, brain.js is powerful, but it's very high level, and you can tell this by how few lines of code it takes. You can configure how large these layers of perceptrons are. Often they're called hidden layers. You can configure how many of them and how large they are, but you can't change finer details. A really good example of this, you can't change out the activation function. So if you're ready to use a lower level library, there's another great library. It's called convnet.js, and it's a great choice. It allows, or it rather forces you, to build the network completely from scratch. So you have to decide how many perceptrons you have on the first layer, how many you have on the second layer, and then how many layers you have. So you have to make those decisions, but that means that you have more power to tune and build that network as it best fits. And when you're ready to use the network, in this case, you just run it forward, similar to brain.js. You're just running that neural network with a particular input. Now, as you can tell from the length of this code, convnet.js is a lot more powerful, and it's also a little bit harder to use if you don't quite understand all the crazy parameters you can tune. So for example, this has you build out every single layer of the network, whereas brain.js will actually generate a lot of it for you using some basic principles. And it lets you change out what the activation function is. So maybe for your purposes, a square wave is adequate as opposed to that more complex hyperbolic tangent. So convnet gives you that power, but it's also more verbose. So really, this is a great option once you understand the underlying parameters enough and your domain enough that you're ready to start throwing this out and get $3.2 billion in funding. So the great thing about machine learning is you really don't have to be a graduate student in artificial intelligence to add some brains to your social network or image sharing site. But you do still need to be a clever coder to extract these useful features for the trainer, because we're limited by time. Neural networks running on millions of pixels will take an eternity to train. So it's your job, in the case of machine learning, to help it out, to give it some better features. So machine learning has an incredibly diverse range of applications. Everything from Google Now to making these subtle UI tweaks are based on converting our rules of thumb and intuition into usable predictions. And thanks to the collision now of academia with open source software, JavaScript 2 can power your smart home, your thermometer, or even your circadian rhythm, or, if need be, your spouse's dinner decisions. And if you guys have any questions afterwards, just hit me up at Nibbler. All those links and stuff, I can also post them on Twitter. So if you guys have any questions.
So you get your normalized output, you serialize all your data, save it into or something. Let's say you want to say, like, this is one of the best results. Like, this has the lowest entropy matching the decision tree. For this item. Are there any good ways to kind of decide, other than arbitrarily, what a good normalized score is? Like what a good match is? Does that make sense?
So let me repeat the question, correct me if I'm wrong. So given a bunch of data, you want to determine how well the decision tree came up, how well it trained after you normalized the data?
So, yeah, so, you know, you build your decision, you say, all right, this is the type of person I'm looking for, thing I'm looking for, build your decision tree, run people against that decision tree or neural network, put them in Lucene, and you get your normalized score for, you know, how well they match your perfect fit, or, you know, what the lowest entropy person is. Is there, you know, I could arbitrarily say if they're above a 0.8, call them like a good match, but is there any way to, other than arbitrarily deciding on that number, kind of calculate where people lie and what a good match is?
So there's a few different parts to that. Depending on the algorithm, the good, really I think the metric you're looking for is how good was the testing results. So in other words, when I ran the 20% of dinner decisions that I hadn't yet seen, how good were the results? Did I get 85% correct predictions? Did I get 90%? Now, how you judge how good that was is probably dependent on other algorithms you tried. Maybe you ran this through neural networks or support vector machines or AdaBoost, and depending on your output from those, you might say, oh, this is pretty good. Really, in machine learning, it's a question of, is it good enough for the task at hand? If it's recommendations on Amazon, they might have a particular cost associated with how good it is. Maybe for every 1% increase in testing accuracy, they get $1,000 more in revenue. But it really depends on the application. Now, the second part of that question, I think, is in the case of neural networks, how do you decide what the actual output is? So neural networks, unlike decision trees, don't output one output. Neural networks actually output they can output a few different things, but most commonly they output a number between 0 and 1 for every potential label that you had. So in the case of Lucy, I think there were like 3 or 4 different things on the menu that you could have ordered from. So you would actually have an output for every single one of those options, and the output would be a number between 0 and 1. And typically that represents the probability that that's the correct label. So if you want to pick whichever label seems most likely, then you would just pick whichever one is closer to 1, whichever one has a higher probability. But again, determining how good your results were is definitely very dependent on the problem at hand. In something like image aesthetics, 70% is incredible because you're dealing with numeric data. If you were dealing with Boolean data, like this image is good, yes or no, 50% would be awful. You might as well make a random guess, and you'd still get 50% accuracy in many cases. So in the case of numeric data like star ratings, 70% is very good for a field that normally you wouldn't think you could put numbers on. Something like Amazon store recommendations, 70% might not be acceptable. Did that adequately answer your question?
You mentioned some idea about using it would be, for example, using the font of a text over a particular image based on the image, on the color of the image. How often is that used? Are any very popular web applications that use machine learning or result of machine learning?
Well, I would say that they definitely do as almost as a background process. So in the case of text over an image, they aren't actively running this training algorithm on every web page you go to, but that was probably used to compute the neural network. So in fact, there are some libraries that let you do this sort of thing. Let me pull up, actually, I wanted to show you guys that demo, if I can figure this out. Here we go. So in this particular example, you actually go through and you select whichever one has the better contrast. And depending on the screen, this changes. But for our case, I say this one is easier, that one's easier, that one's easier. Then we get to this one, and it's kind of a tie. That one's easier. And that actually produces results very similar to a mathematical formula someone put together. But to come up with that mathematical formula, they actually did this sort of process. So you may not see machine learning algorithms running on the front end. It's much more likely to be on the back end. You know, if Amazon was running a Node.js back end and they were trying to come up with user recommendations because their engine wasn't doing so well, then they would do something like this. I don't think they're on JavaScript, but if they were, they would do it. And thankfully, JavaScript now, if you're using something like asm.js and you're using these subsets, you can get speeds that are about 2 times native, as I recall. So it's a very feasible platform for doing machine learning, but you probably won't see it on the front end directly. It's going to be the results. There's another really common example of this. If you happen to be on a photo sharing site and a lot of times users submit pictures that are way too big and it has their face in it, and using some of these composition rules, it will try to find the face, which is usually based on Haar wavelet detector. That's actually another machine learning algorithm result. And it will try to find it and try to put it on a rule of thirds or something like that and try to crop it down. The front end won't actually be computing that. It won't be analyzing the image, trying to find the face and figure out where it should go. It will probably have pre-computed on the server side, and the server side will say, okay, as this space gets more and more constrained, where should the face be? So it's more often you're going to see it pre-computed. Was there a question back here? Mm-hmm.
So I have a question about how to manage the quality of the training set. So for instance, you can have a feature that's relatively rare in the population of examples you have, right? But maybe is it important to classify things?
That is a great
Is it
question.
better to have that sort of represented as like its relative size of the population? Would you want to over-represent your training set because you want to have you want to have enough instances of it to generalize? See what I'm saying?
Yes, this is actually one of the more interesting nuances of machine learning. So whenever you're dealing with a data set that has some important feature, but that feature occurs very infrequently, sometimes what you'd like to do is maybe cut down on the number of, you might want to cut down on the other examples, but at the same time, that's not so good either. So what it turns out, some algorithms are better at this sort of thing. So something like AdaBoost. AdaBoost is actually, I think, canonically one of the best examples of an algorithm that can start from something that occurs very infrequently, starts from something that occurs very frequently and trains very well for it, and then begins to find these more subtle occurrences. Maybe it finds the 1 or 2 cases where Lucy ordered lamb chops, whereas she never would have before. So something like AdaBoost is very good at that sort of thing. The key assumption in machine learning, though, is that the data that you see in the future should be probabilistically sampled from data you've already seen. In other words, if Lucy has a personality change and she starts ordering things on completely different premises, your previous training is no longer useful. So you have to assume that whatever you're training on has the exact same probabilistic distribution as what you had when you were training it. So what that means is if you intend to get very few of these unique features in the future, then that's exactly what you have to use to train, because otherwise the algorithm will be a little bit over-prone to suggest it. The problem is that a lot of algorithms won't ever pick up on it. They won't notice the nuances, and they'll think it's just noise or overtraining. That's where different algorithms perform better. If you have a very normalized data set, most algorithms do well on that.
Looking for sort of like a continuum of problems that happen very easy and very hard to fix, so that we know, like, say I have a problem and I know how much money or time to expect it to take using some tools.
So how would you describe that? How are those problems described? As like a story and pivotal tracker, or maybe I didn't quite understand your question.
Like a couple examples of things like in the past couple of years that have been very easy to solve, and a couple examples of things that have been very difficult to solve, or are in the process of, you might know, people are trying to solve right now. So if somebody has a problem, they would know what to expect, how long that would take, or how much money that would take. Does that make sense?
A big part of machine learning is actually dedicated to unsupervised learning. So unsupervised learning is kind of where all the research people go. Whereas supervised learning, it's just these algorithms, and you could just try to throw out a problem, and you would just experiment maybe for a few weeks or a month in something like Weka, and you'd throw a bunch of data at it and see which algorithm does better. Sometimes, however, you want a machine to actually be able to figure those things out on itself, and that's more unsupervised learning. unsupervised learning can take years because essentially, ironically, it's called unsupervised, but you actually watch the output of the algorithm and try to see if you can understand the underlying data. So unsupervised learning is very common when you don't understand the domain. You can't figure out what features contribute to what. So this is really common if you're dealing with numeric data over a time sequence. It's really hard, for example, to look at a person's heartbeat spike and determine if they're about to have a heart attack, perhaps. And that's the sort of thing computers can do really well because they can understand the nuances. So depending on the problem at hand, it may take weeks, it may take years in research. Well, I'm out of time. I have to cut out, unfortunately. But if any of you guys have any other questions, I'll just be out here.